Hello all. Again welcome to first PUC online classes. Let us discuss the continue on thermal conductivity of composite slabs. In previous class we came up to the thermal conductivity of composite slab in series combination. We obtain how to obtain the common temperature at the interface along with the equivalent thermal conductivity of two composite slabs in series. Now in this session let us discuss thermal conductivity of composite slabs in parallel combination. Shall we see here? Thermal conductivity. Thermal conductivity of composite slab. Composite slab. Slab. See here. Now let us discuss on parallel combination. Parallel combination. Composite slab in parallel combination mean the two are different rods of a different nature of same length but of a different area. If they placed one by one, then this combination we are calling combination of slabs in parallel. How they looks like? Look at me here. I will take two different materials of different area of cross section but having same length. Look at me here. Shall I take? This is nothing but one slab. I can take one slab of area of cross section. How much? Area of cross section is A1. Thermal conductivity how much? A1. And it is second slab of thermal conductivity A2 and the area is equal to A2. But both rods having the length L. Both are connected here. Right. Now let us take theta 1 represent temperature of rod 1 and theta 2 represent temperature of rod 2. Right. In parallel combination, the length of each composite slabs remains same. Along with in parallel combination, the heat current divides across each slab. We have learned that in series combination, the heat current remains same, but here heat current divides. How the heat current divides? The total heat current is nothing but the sum of heat current across each slab. We know that the heat current, the rate of flow of heat, that we are calling heat current. Now let us calculate the equivalent thermal conductivity of this combination. For one slab thermal conductivity is K1 and for a second slab thermal conductivity is K2. Right now, shall I go for slab 1? For slab 1, how to write the heat current? Look at me. Initially what I said, in this case the heat current divides and total heat current equal to sum of the heat current across each combination. Look at me here. For one slab I will write. For one slab the amount of heat flow Q1 directly proportional to area A1, directly proportional to difference in temperature how much? Theta 1 minus theta 2. Right. Directly proportional to time elapsed and inversely proportional to length of the rod. For one slab according to laws of thermal conductivity. We can call these are laws of thermal conductivity when heat transfer from one end to another end. Now or can call the amount of heat transfer Q1 equal to some constant K1 into A1 into bracket how much? Theta 1 minus theta 2 into T whole divided by how much? L. Or you can write the heat current is the rate of flow of heat Q divided by T equal to how much? K1 A1 into bracket theta 1 minus theta 2 whole divided by L. Right. Rate of heat flow, this we are calling heat current. For one slab I will take heat current as H1. Then again how to represent K1 into A1 into bracket theta 1 minus theta 2 whole divided by L. Shall I call this equation number 1? For one slab, For this slab the heat current given like this. Then similarly for second slab of area A2, thermal conductivity K2, how to represent the heat current here? Shall I take H1 can be replaced by H2 and K1 can be replaced by K2, area is A1, A1 can be replaced by A2 and temperature again theta 1 minus theta 2, but length of the rod remains same. Always the length of the rod remains same. Shall I call this? This is nothing but equation number 2 now, right? But here how to represent the total heat current across this combination? Total heat current. The total heat current just I want to represent by the quantity H. Quantity H. K2 or K1 I will replace by what value? K. Replace by K. And A or A1, A1 or A2 replace by total area of this combination. What is total area of this combination? How much? It is A1 plus A2, right? And theta 1 minus theta 2, keep it up same, whole divided by how much? Length. Shall I call this now equation number 3? Right. H we are calling total heat current. I said that already in parallel combination the total heat current is nothing but the sum of heat current across each combination. That is total H is equal to H1 plus S2 in parallel combination. Shall I write? For parallel combination. For parallel combination the total heat current can be replaced by H. Total heat current is equal to sum of heat current across each combination. Remember this. In series combination there was common temperature T or common temperature theta we can call, but in this case there is no common temperature across the junction. Here there is no common temperature because they are connected in parallel. Now from equation 1, 2 and 3 what you are getting? Equation 3 is nothing but H. Shall I represent? K is nothing but equivalent thermal conductivity into bracket how much? A1 plus A2, A1 plus A2 into bracket theta 1 minus theta 2 whole divided by how much? Length L equal to H1. H1 mean equation 1, how to say? K1 A1 into bracket theta 1 minus theta 2 whole divided by length L, right? Plus H2. H2 mean K2 into bracket A2 theta 1 minus theta 2 whole divided by length L. Are you following me? Now from this side and this side what are common values? Theta 1 minus theta 2 is common, L is common. Here also theta 1 minus theta 2 divided by L is common. Here also theta 1 minus theta 2 divided by L is common. They get cancelled, theta 1 minus theta 2 divided by L on from both sides. Then what is remaining? K into bracket how much? K into bracket A1 plus A2 equal to what is remaining? K1 A1 plus K2 A2, or equivalent thermal conductivity K can be replaced. K can be replaced by K1 A1 plus K2 A2 whole divided by A1 plus A2. This is equivalent thermal conductivity. The equivalent thermal conductivity when different rods of different nature of same length, if they are connected in parallel, then equivalent thermal conductivity can be given by this equation. For parallel combination, what is the condition? Length of two rod must be remain same and current must be divided across each combination, and the total current is sum of current across that current. What current here? Heat current across each combination. If the case here what is same? Length is same. If the case length is same and area also same, then what about equivalent thermal conductivity? For two rods I am taking. See here, if the case the rods having different area now having the same amount of area. If the case, if A1 equal to A2 equal to A, then what about equivalent thermal conductivity? Shall I represent? K equal to, right? K1 keep it up same. Now A1 equal to A2 can be replaced by A. Again K2 can be replaced by K2. A2 can be replaced by A whole divided by how much? A1 can be replaced by A, A2 can be replaced by A. Then what about this value? Equal to how much? Equal to K1 plus K2 into A whole divided by how much? 2A. A get cancelled. Then what is equivalent thermal conductivity? Equivalent thermal conductivity is equal to K1 plus K2 whole divided by 2. Equivalent thermal conductivity. For 2 rods, if 3 rods are there, then K is equal to K1 plus K2 plus K3 divided by 3. If 4 rods are there, K1 plus K2 plus K3 plus K4 divided by 4. Like this, how to represent? For N rods, no matter, not only 2 rods, you can connect number of rods. For number of rods, how to write equivalent thermal conductivity? K1 plus K2 plus K3 up to Kn divided by N. So these are the concept concerned to thermal conductivity. I mean, the transfer of heat takes place in the solid by method of conduction, and by conduction we already have learnt about the regarding thermal conductivity. After this, let us see the one more mode of heat transfer that we are calling convection. That concept we will see now. The concept of convection. Right. Concept is convection. Convection. See here, this is the one of the mode of heat transfer which takes place in liquid and gases. Liquid and gases. In gases or liquid, if heat is given, then heat transfer from one region to another region. How heat is transfer? Heat transfer from hotter end to colder end due to actual momentum of liquid particles. Then how to define the convection? Convection is the process of transfer of heat from one part of the liquid to another part of the liquid with actual moment of its particle. This process we are calling method of convection. How to see? In liquid or gases, the heat transfer from one region of the liquid to another region of the liquid due to actual momentum of liquid particles. This process we are calling the convection. Now, how the convection is possible? To understand the concept of convection, let us take the vessel containing the liquid. Shall I take here? I will take the vessel containing liquid. See here, this is the vessel. This is the vessel containing liquid. Look at it. This is the level of liquid. This is the level of liquid. Level of liquid in the beaker, right, or in the vessel. To this liquid, I want to provide the heat source. Look at me here. Here I want to provide the heat source, right? This is the heat source I want to provide. When heat provided, the heat transfer from one part of the liquid to another part of the liquid with actual momentum of particles. With actual momentum, how the heat is transferred? Students, we know that if a temperature of the liquid increases, definitely density decreases. Density decrease means it becomes lighter. Definitely it becomes lighter. Here how the convection is possible? Convection is possible when heat is provided to liquid at the point of contact of the heat source. The molecule getting the maximum amount of kinetic energy, as a result it get expand due to absorb large amount of heat. Due to expansion, its density decrease, it becomes lighter. The lighter molecule, it goes upside and transfer heat energy to colder part. As a result, the lighter particle comes up and rise up, transfer heat energy to this upper molecule. The upper molecule gets the energy, again it will rise up. Actually, how it happens? The bottom molecule absorb amount of heat energy, and due to absorption of large amount of heat energy, its density becomes smaller. Density becomes lighter. As a result, this molecule will rise up. When molecule rise up from one place to another place, it can transfer heat energy to upper molecule. Similarly, when heat transfer from one part to another part, a current is set up in the liquid. Current is set up in the liquid. That current we are calling convection current. How the convection current possible? When molecule transfer from one part to another part by absorbing large amount of heat energy, a current is set up in it. This is the current. This current we are calling convection current. Convection in what direction? This direction. This direction. A current is set up. This current what you are calling? This current we are calling convection current. Convection current. Right. This convection current, it flows in the liquid still. The temperature of all part of the liquid must be same. Up to this current flows. ಈ ಕರೆಂಟ್ ಎಲ್ಲಿಂದ ಫ್ಲೋ ಆಗ್ತದೆ ರೀ? ಯಾವಾಗ ಎಲ್ಲ ಪಾರ್ಟ್ ಆಫ್ ದ ಲಿಕ್ವಿಡ್ ಸೇಮ್ ಟೆಂಪರೇಚರ್ ಅಟೆನ್ ಆಗ್ತದ, ಅಲ್ಲಿ ತನಕ ಏನಾಗ್ತದ ಈ ಕನ್ವೆಕ್ಷನ್ ಕರೆಂಟ್ ಏನಾಗ್ತದ ಸೆಟಪ್ ಆಗ್ತದ ಲಿಕ್ವಿಡ್ ಒಳಗೆ. ಹೌ ದಿಸ್ ಈಸ್? How current is set up? Convection current set up. The bottom molecule which is contact with the heat source, it absorb large amount of energy. As a result, expand. Then density decreases. It rise up. The raised molecule transfer heat energy to upper molecule. Then the convection current is set up in the liquid. This is how the convection possible in case of liquid, and convection also possible in the gases also. But look at students here. For liquid, if heat is given, definitely heat transfer from one part to another part. But when the hot liquid placed in the surrounding, definitely heat transfer from hot liquid to surrounding. Rate of cooling. When a hot liquid placed on the table, after some time it becomes cool. It becomes cool means it loses some amount of heat to the surrounding. We know that. When hot system made physically contact with cold system, definitely heat transfer from hot system to cold system. Newton provided the very famous law. The law is nothing but Newton's law of cooling for liquid and solids. A hot liquid placed in some other system, it becomes cool. The cooling of hot liquid versus time and versus temperature, it is given by the Newton's law of cooling. Now our concept is we will concentrate on a Newton's law of cooling. Later we will go the one more type of heat transfer that we are calling radiation. Let us move for Newton's law of cooling. Right. To understand the concept of Newton's law of cooling, we will take a liquid. Newton's law of cooling. Newton's law of cooling. To understand this concept, shall I take a liquid, the containing vessel, the vessel containing the liquid? Shall I take here? I will take a liquid. This is the liquid I will take. Right? This is the liquid. This is the level of liquid. Level of liquid. Right. Consider this liquid is hot. Shall I take? The temperature of this liquid is equal to theta. I will take. Theta I will take. And the temperature of the surrounding. Shall I take the temperature of the surrounding? I will take theta naught. Theta naught represent the temperature of surrounding. Theta represent temperature of hot liquid. We know that when hot liquid placed in surrounding, the heat transfer from hot to surrounding, hot liquid to surrounding. Here temperature or heat transfer from hot to surrounding, system to surrounding. When the liquid loses the heat, Newton's provided the very famous law. That is Newton's law of cooling. The Newton's law of cooling says that if the temperature difference between the system and surrounding is not much more greater, then the rate of heat loss is directly proportional to temperature difference between system and surrounding. ಏನು ಹೇಳಿಕತ್ತೀನಿ, ಒಂದು ಸಿಸ್ಟಮ್ದ ಟೆಂಪ್ರೇಚರ್ ಅಥವಾ ಸರೌಂಡಿಂಗ್ ಟೆಂಪ್ರೇಚರ್ ಡಿಫ್ರೆನ್ಸ್ ಭಾಳ ದೊಡ್ಡದಿರಲಿಲ್ಲ ಅಂದ್ರೆ ಆ ರೇಟ್ ಆಫ್ ಹೀಟ್ ಲಾಸ್ ಅದಕ್ಕೆ ಡೈರೆಕ್ಟ್ಲಿ ಪ್ರಪೋರ್ಷನಲ್ ಇರ್ತದೆ ಟೆಂಪ್ರೇಚರ್ ಡಿಫ್ರೆನ್ಸ್ಗೆ ಇರ್ತದೆ. ಯಾವ ಟೆಂಪ್ರೇಚರ್ ಡಿಫ್ರೆನ್ಸ್ಗೆ ಇರ್ತದೆ? ಸಿಸ್ಟಮ್ ಮತ್ತು ಸರೌಂಡಿಂಗ್ ಇರ್ತದೆ. Your liquid is a system and this one is the surrounding. Air is the surrounding. What Newton's law of cooling says? Shall I write the Newton's law of cooling statement? If temperature difference is not much greater between system and surrounding, the rate of heat loss directly proportional to temperature difference between system and surrounding. Simply, how to say? If the temperature difference between system and surrounding is not much greater, the rate of heat loss is directly proportional to temperature difference between system and surrounding. How this is? Shall I take? If the temperature of this hot liquid must be 70 degree or 65 degree, then temperature of the surrounding must be 30 degree. There is not much more difference. Difference must be lying from 40 degree to 60 degree or 40 degree to 35 degree. See here, what Newton's law of cooling says? The rate of heat loss dq divided by dt, rate of heat loss is directly proportional to temperature difference between system and surrounding, provided temperature difference is not much more greater, or the rate of heat loss must be equal to some constant into temperature difference. I will put the negative sign. Where the negative sign indicates as the time passes the rate of heat will be losses. I mean as the time passes the temperature decrease. Your negative sign indicates as the time passes the temperature decrease. And the constant K we are calling Coulom's constant. We are calling Coulomb constant. Now shall I call this? This is the equation number 1. But the amount of heat transfer from system to surrounding, we know the amount of heat transfer. How the amount of heat transfer? The amount of heat transfer dq directly proportional to mass, directly proportional to temperature difference. I will take a d theta, or the amount of heat loss equal to some constant specific heat capacity into change in temperature. What is delta theta? Delta theta indicates the small change in temperature of the system. Now divide this equation by dt on both sides. What you will get? See here, I will take dq divided by dt equal to mass c into d theta whole divided by dt. Shall I call now? This is the equation number 2. I can call. Now just compare equation 1 and 2. Here also dq by dt, here also dq, here also rate of heat flow, here also rate of heat flow. Compare equation 1 and 2. What you are getting? If you compare equation 1 and 2, shall I write this? How to write? Mass C into d theta divided by dt equal to how much? K into theta minus theta naught. Don't confuse here. Theta represent temperature of hot liquid, theta naught represent temperature of surrounding. Then what is a d theta? D theta indicate the small change in temperature during cooling. Right? Now again from this equation, how to write? From this equation, shall I take? From this equation I can call d theta divided by how much? Theta minus theta naught equal to K divided by m into C into how much? dt. Or I can call d theta divided by how much? Theta minus theta naught. Theta minus theta naught equal to this small k. I will take now constant as capital K into how much? dt. Right? Now integrate this equation on both sides. Integration mean what to do here? Shall I take integration of 1 divided by theta minus theta naught into how much? d theta. Here k is constant, capital K is constant. Integration of how much? dt. It is of the form integration of 1 by x into dx. Integration of 1 by x into dx is equal to log to the base e of x. So how to replace this? This can be replaced. Integration of this value 1 by x into dx form log to the base of how much? Theta minus theta naught equal to capital K is constant, integration of dxx form, integration of dt is equal to t. So from this you can get the cooling of liquid. From this equation, if you plot two graphs, temperature versus time, and log to the base of temperature versus time, we will get the two graphs by practically. How to get actually? If you plot the time along x-axis and the temperature along y-axis. Shall I take here? Look at me. Along x-axis I will take the time and along y-axis I will take the temperature theta. As the time increase, if the time increase, then what about temperature? Temperature gradually decrease of the hot liquid. How to represent? If the time increase, gradually the temperature is decrease. Right. Then one more graph practically we can obtain. Again take the time along x-axis and log to the base e of theta minus theta naught along y-axis. The graph will be a straight line with a negative slope. We can obtain experimentally. We have one famous experiment for first PU, that is Newton's law of cooling. How the Newton's law of cooling can be obtained? Let us take the hot liquid placed in the calorimeter and placed a thermometer. Now let it be the temperature of the hot liquid is 70 degree and the hot liquid in the calorimeter is 3/4 of the calorimeter. After some time the liquid start to cool. If we note down after 2 minutes after 2 degree change in temperature, or if we plot after 2 degree cooling in temperature, if we obtain the graph versus time, we will get these two graphs. One is time versus temperature, the second one is log to the base e of theta minus theta naught divided by t. So this is Newton's law of cooling. But the Newton's law of cooling, it is useful to solve some numerical. On what basis? Look at me here. Remember these two formulas. What are those? Log to the base of theta minus theta naught is equal to k into t. And this formula, amount of heat loss is equal to dq by dt is equal to k into theta minus theta naught. But the Newton's law of cooling, again you can modify. How to modify? See here. How to modify the Newton's law of cooling now? See here. Look at me. What to do here? Now I will take, see here, theta represent temperature of the hot liquid and theta naught represent temperature of surrounding. Right? According to Newton's law of cooling, what it says? The rate of heat flow directly proportional to temperature difference between system and surrounding. Shall I add the Newton's law of cooling statement? Rate of heat loss dq divided by dt directly proportional to temperature difference between system and surrounding, or I can call dq divided by dt equal to constant k into theta minus theta naught, right? Now listen to me, students, here. Now I can call it as equation number 1, where I will put the negative sign indicates if temperature increase, if the time increase, then what about temperature? The temperature of the system here must be decreases. Now I will take alternating manner here. Let us take the liquid cools from theta 1 to theta 2. Liquid cools from theta 1 to theta 2. Actually, what is theta? Temperature of the hot liquid. Theta naught represent temperature of the surrounding. If the liquid cools from theta 1 to theta 2, then shall I represent here? If the case liquid cools from theta 1 to theta 2, how to represent rate of heat loss? When it cools from theta 1 to theta 2, the rate of heat loss can be given dq divided by dt of how much? Theta 1 minus theta 2 divided by time t. I mean, the temperature of the hot liquid decreases from theta 1 to theta 2 in this time interval. Then what is theta here? Theta represent average of theta 1 and theta 2. Are you following me? What I said? If the temperature of the hot liquid changes from theta 1 to theta 2, then rate of heat loss can be given in this time interval. Koಟ್ಟಿದ್ದ ಟೈಮ್ ಒಳಗೆ ಎಷ್ಟು ಲಾಸ್ ಆತ್ರಿ? theta 1 minus theta 2 ಲಾಸ್ ಆಯಿತು. But theta ಅಂದ್ರೆ ಏನು? Average of theta 1 and theta 2. Shall I take here directly? Now I will call it as equation 2. Very simple. Compare equation 1 and 2. What you are getting? If you compare equation 1 and 2, I can take theta 1 minus theta 2 whole divided by time equal to k into how much? K into theta minus theta naught. Where theta is what? Average of this value. Average of theta 1 and theta 2. If I put this value, what is theta here? Theta represent average of this value. Theta 1 plus theta 2 whole divided by 2. Then what about this equation? Shall I take this equation? How to represent? Theta 1 minus theta 2. Theta 1 minus theta 2 whole divided by t equal to how much? K into bracket. What is theta? Theta 1 plus theta 2 divided by 2 minus of how much? Theta naught. So this is alternating form of Newton's law of cooling. This is useful to solve so many numericals during cooling of hot liquid. How to take an example? How to take an example for this modification of Newton's law of cooling? I will take a hot liquid, right? The hot liquid changes its temperature from theta 1 to theta 2. For that, shall I take here? Now, shall I see students here? I will take a hot liquid. This is the hot liquid I will take, right? Hot liquid I will take. Shall I take the hot liquid here? The hot liquid, it cools 85 degrees Celsius to 75 degrees Celsius in 10 minutes. Shall I take 85 degrees Celsius to 65 degrees Celsius? Shall I take here? If the case it cools from theta 1, shall I take theta 1 is equal to 85 degrees Celsius? It cools from where to where? It cools from theta 2. How much? 75 degrees Celsius in how much interval of time? 10 minutes. 10 minutes. I mean, liquid cools from theta 1 to theta 2. But if the liquid cools from, shall I take? If the liquid cools from theta 3 is equal to 75 degrees Celsius and theta 4 is equal to 65 degrees Celsius. How much amount of time is taken? Are you following? ಅಂದ್ರೆ ಒಂದು ಲಿಕ್ವಿಡ್ ಎಲ್ಲಿಂದ ಎಲ್ಲಿ ಕೂಲ್ ಆಗ್ಯದ 85 ದಿಂದ 75 ಡಿಗ್ರಿ ಕೂಲ್ ಆಗ್ಯದ ಎಷ್ಟು ಟೈಮ್ ಒಳಗೆ 10 ಮಿನಿಟ್ ಟೈಮ್ ಒಳಗೆ ಹೌದ್ರಿ ಹಂಗಂದ್ರೆ ಅದೇ ಲಿಕ್ವಿಡ್ ನಮಗೆ 75 ದಿಂದ 65 ಡಿಗ್ರಿ ಕೂಲ್ ಆಗ್ಯದ ಎಷ್ಟು ಟೈಮ್ ಒಳಗೆ ಅದನ್ನು ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಿ ರಿಮೆಂಬರ್ theta naught I will take. Theta naught represent temperature of surrounding, it is 70 degree or 30 degree I will take, no matter, 30 degree Celsius, right. For theta 1 and theta 2 initially I will solve the k value. Shall I solve here? How to go? Look at me. From this theta 1 and theta 2, what is theta 1 85, theta 2 75, t is equal to 10 minutes. Shall I solve here? Theta 1 minus theta 2, theta 1 is 85, theta 2 is 75, whole divided by time is how much? 10 minutes, equal to k is constant, I don't know this. Theta 1 how much? 85 plus 65 whole divided by 2 minus theta naught is 30 degree. Then from this k is equal to how much? It is 150. You solved k now, right? It is for theta 1 and theta 2. Shall I write for theta 3 and theta 4? This equation how to modify? Hang modify modbodri? Shall I take here only? Theta 1 replaced by theta 3, theta 2 replaced by theta 4. I don't know this time. Shall I take this time t dash? Equal to k into bracket how much? Theta 3 plus theta 4 divided by time minus of how much? Theta naught. Theta 3 how much? 75. Theta 4 how much? 65. I don't know this time t dash. Equal to 1k is equal to 1 by 50 into bracket theta 3 75, theta 4 65 whole divided by t minus theta naught how much? 30 degree. Solve this. If you solve this, what time you are getting? T dash is equal to 12.4 minutes you can get. 12.4 minutes. I mean, to cool the hot liquid from 85 to 75, it takes the time 10 minutes. But the same liquid, it cools from 75 to 65, it's take a 12.4 minutes. The remaining concept we will see in the next class. Thank you, students.